Okay, next up, the day I reverse engineered a Game Boy Advance game by Macabeus and Matheus.
Zdravo, ja sam Matej, and that's all the Serbian I got for you guys today. We came a long way from Brazil, so it's like this is our slide, and we are here to bring you soccer, caipirinha, and carnival. Not really, but just this game, which is very, very funny one about Brazil. And when you see that things are getting a little bit boring because of the technical side of the talk, we are probably going to use it anyway. So yeah, the day we reversed engineer a Game Boy Advance game. So it's a bit of a storytelling here, so how it all started. But I'd really like to know a little more about you guys, so let's do the raise your hands thing. So, yeah. Who here has done some reverse engineering before? Oh, less than half of you guys. Cool. And reverse engineering a game? Yes. Oh, like 3 of you. No, 3 or something. Cool. And last but not least, who here has ever done some web development? Not that related. Cool. Cool. Really cool. So, still raising your hands. Who knows the thing on the left? Yeah, on the right. It's called Klonoa. And yeah, many people don't know actually, but you certainly know Game Boy Advance, which was a very, very popular game console back in the early 2000 years. And our story starts like this. This was Macabeus, and this was me. And this was us playing Klonoa on our emulator. And this was us bored, basically because he wanted more levels to play with, and I wanted different levels to play with. So, yeah, some mad science going on here. Oh, by the way, this is Klonoa. And for those who don't know Klonoa, it's a tile-based puzzle game. It's a nice one, but it's also very, very short. You have basically 3 levels to play with. And some people, mostly like him, they just would love to play it more. So we thought, what if we could create our own levels, or maybe what if we could make the ones that exist more interesting actually. And as I told you, Game Boy Advance was very, very popular, so many people wrote many manuals and tutorials and softwares to study its architecture. So it's very, very well documented, so it was a good way to start doing some reverse engineering. So this is how CloudGBA.js was born. And basically it's open source on GitHub. You can go to this link, which you probably can't read, but it's over there. And it's a web app written in JavaScript and C, where you can edit the levels that you have on Klonoa. But let's go for the challenge. And it all started with Stretch and Bridge because, you know, we had no previous experience in doing reverse engineering, so creating a level editor just sounded like a very, very abstract thing for us. We had no certain path to follow. We didn't know where to begin. So we thought, and also in reverse engineering in general, it's easier for you to just edit something that already exists than trying to create something from scratch or trying to delete some elements. So we had a bridge in the first level and we wanted to stretch it. And we had our tools. The first one is called NoCacheGBA, and it's very useful for doing dynamic analysis, which is basically analyzing the code as you are playing the game. And the other tool was called IDA. This one is more popular. Some of you have probably heard of it. And we used IDA because actually NoCacheGBA lacks more powerful tools for doing static analysis. And IDA brings tools like graphic visualization of the assembly code, and also it allows you to extract some part of memory to certain files, and even basic stuff like commenting lines of code you can also do with IDA. So this is how it looked like. On the left side, NoCacheGBA, and on the right side, IDA displaying some assembly code. We were running a virtualized Windows. So let's start to start the bridge. Here we are on the first level, and this is the bridge that we want to stretch. And this panel is actually a feature of NoCache GBA, and you can see many details of the tiles that you have on the screen. And on this panel, we can see the tile ID for this part of the bridge, because on a tile-based game, each part of the map is composed of tiles, and each kind of tile has got a very unique ID to identify what is it, basically. And in the case of this part of the bridge, the tile ID is 9B, and the part of the continuous part of the bridge is called 9A. And there is another very important information this panel's got, which is the address. In our case, it tells that the address is for this tile is 0600F1AD. And actually, it comes as no surprise that we have this address, because, as I told you guys, there's so many documentation on Game Boy Advance, and one of those documents is this manual, which describes in deep detail its architecture. And there's a section explaining how the memory works, and the memory have many regions. Each region has a very important purpose and very unique size. And the address that we found is on a region called VRAN, which basically stands for Video RAN. And the purpose of this region is to store the sprites and backgrounds and all those things. So it was no surprise that we found this. And if we try to visualize, this is where our bridge starts. So it looks like this. And okay, it was good, because when you're doing reverse engineering, every time some piece of information makes a little sense, you get happy. So then we grow it bigger, and we run a frame it after we did it, and we can see the new part. And this is exactly where our first what the fuck moment happened, because when you run a frame after you did it, you see that the new part is no longer there. So understanding what's happening requires us to understand a very important concept called DMA, and I guess you can tell us a little more about that.
Yes. Yes, Matthias, this behavior makes sense, and in order to understand why it makes sense, we need to understand the DMA. Well, moving closer to another place of the level, we can see that the entire tile map changes on video run. So we can note that it will only store what the player has to see from somewhere else that has the entire tile map. But where is the entire tile map stored in order to send the information to video run for each frame? There is a book that explains many details about the internals of GBA, and in the tiles map chapter, it contains an important concept: direct memory access, DMA. This is a feature of computer systems that allows set hardware to access main system memory regardless of the CPU. Using other words, it provides a way to copy and paste faster. It makes sense because the video run is too small to install the entire tile map. Then it's necessary to install the entire tile map on another memory region and send a part of it to video run. And NoCache GBA has a feature that allows to track the DMA communication. Run one frame on the game, we can see that it made 4 copies. And on this result, this is the closest to the base of the bridge. And in this area of the visual run data source, and it's the address of the visual run data source. So GBA replaces the visual with the data started from this byte, which is located in a region called fast double run, this larger one. So instead of change the byte at the visual run, we need to change the bridge byte at the fast double run. Let's go to address. And our bridge starts here. Nice. So let's switch it. Since DMA will send the tile map data to visual run on each frame, it will work now, right? So let's see. Now it's working, but watch. We can see the tiles that are on the screen, but we can't stand on them. It's crazy. Why it's happening? Doing a very simple test, walking to a large part of the level, we can see that all tiles disappear when out of the play visual range. So there is another place of the memory that will store the tile map and is the data source of the fast double run. But where is it? Since I don't really know where the entire tile map, neither a better way to find it, I choose to understand better how the physics works on the game. If we understand how the physics works on the original tiles, we can copy these behaviors to our tiles. Before understanding what attacks the clones on the floor, we need to approach another important feature of GBA, the Object Attribute Memory. The abbreviation is just OAM, and I use it now from on. Since the GBA is a hardware to play games, it has many features to work well with games. One of these is OAM. Each object on OAM looks like a tile, but you can move it, change its sprites, size, and use a tool from GBA. We can see the address in which node is stored on the memory. It's stored at this number. Read again the GMA logs on GBA. We can see exactly the byte that writes on Clonoa's object. So the bytes from this address are copied to Clonoa's objects, and the value on object that defines the Y position is the first. So we need to track the chains on these bytes as 03004800. A very simple and useful test that I made to check if I am going the correct way was change this byte and run a frame. And doing it, we can notice that it changes, but for just one frame, because on the next frame, we will continue to fall from the previous position. So we can notice that we are going the correct way, but we need to find the data source of this byte. So let's see some important assembly instructions that change the value of this byte. On the first part, we can see some assembly instructions written in ARM. And on the second part, we can see the memory. The highlighted byte is the Y position of Clonoas. After these instructions, all bytes on this memory region are replaced by trash, including the Y position. And many instructions after that, the Y position is replaced by the new value. But how? How did it work? Since we have just trash on the memory, how did the code calculate the new Y position? To understand it, we made some crazy reverse engineering using both tools, GBA and IDA. With this analysis, I found an important detail. The bytes that was falling from object address are used to set the Y position of the camera, but the bytes on the left are used to set the global Y. For example, you can see that Clonoas is on the same height to the camera, but so these values are the same. But since it's on a higher position on the level, this value is lower. So we need to follow this byte to understand how it's updated. Run a step-by-step debugger, we found the moment when this value is updated. It's happened on this assembly instructions in this block, and the decision of whether it should update or not is made in this upper block. Zooming in this upper block, we can see how it decides whether the Y position should be updated or not, and thus instructions use a tile ID stored in another memory region, the slow double run. This another memory region is bigger than the fast double run, so the game can store the entire tile map in this memory region. So we should add our tiles to slow double run, because it's the data source of fast double run and video run. And do it, our tile really works. We can stay on it, and our tiles don't disappear when they are outside the play vision. Very nice, it's working. But okay, very nice that we can create real tiles on the game, but we need to create an amazing level editor on browser. So we need to find the tile map on the ROM to be able to extract it and deploy it on the browser. It's one of the most important reasons that one should have at these projects. Why the information flow has this way from the cartridge to slow double run, to the fast double run, to visual run, to display. We are walking on the reverse way. Use the clues that we are finding on the path to walk from display to slow double run. And because there isn't any memory region before slow double run, we need to use the chips to find where's the tile map on the cartridge. So let's run the step-by-step debugger to see the instructions that writes on the tile map at slow double run. And we find these instructions as SWI11.8. But what the fuck is it? So let's talk about SWI instructions. This software interrupting. Well, some guys call it BIOS calls. Well, BIOS is a firmware that is intended to initialize the physical components of the system. In GBA, it's BIOS exposes many functions often used in games, including data compression and decompression. Each function has an associated numeric code, which must be used as parameter in the SWI statement. For example, there is a SWI code to use the divide operator. To call it, you just need to use the SWI with the number 6 and send the parameter to the registers. The R0 is the numerator and R1 is the denominator, and the output of the divider will be saved on the registers. Besides the divide operator, we can also call some compression and uncompression operator use the SWI instructions. For example, here the game is called Huffman and LC77 algorithms. And the Huffman and LC77 is the deflate algorithm. So this game, when it's loaded a level, uncompress each using the deflate algorithm and save the result on slow double run. From the parameter with the address of the memory data, we can see the compressed data of the level. Either is so awesome that you just need to push the cursor at the address and will show the entire blob of the level. And you can use a filter of either to export this data to a separated file. Okay, now we have a file with the compressed data of a level. Then we need to uncompress it, use the same algorithm. Do you remember that Matthias said that Game Boy Advance was a very popular console and many people made awesome tools to work with it? So a person made a few years ago an open source tool written using C with the same algorithm and implementation of the compression algorithm of the GBA. In order to use it, we just need to send a file path to this software, then it will uncompress the file. And use it, we can notice that this batch from cartridge and from the uncompressed file are the same. Very nice. Just drink some. Well, okay. Now we know where the tile map is stored, and we have a file with this data. We want to build a level editor, so we need to paint this tile map to be able to edit it. But we have an additional challenge. We have just a vector with this data, and we need to plot it at a bidimensional array, right? For example, all the plots are valid, but just one of these are used on the game. So we need to find the correct one. Where is the new line in the array? And we have an important clue to help us, the size of the buffer. And probably the height and the width are natural numbers because it doesn't make sense a half tile. So we just need to find the height or the width, and we will find all the variables. Think with me, I am on the tile A, and there is a tile B exactly below A. From the tile A to B, there are 9 bytes, so there are 9 tiles. So the length of the tile map is exactly 9. We can reproduce the same idea on the game to find the length of the level. Firstly, we need to get the address of a tile. To get it, we need to set a breakpoint in this function, so we can see the address of the bridge tile on the register R0. Then we need to mark this tile, change it. So we should change this byte. This is our tile A. Then we need to drop clonal one level below in order to get the address of the tile of the second level. To do it, we just need to change the tile below him to 0, 0. And we can see that clonal is one level below now. And as the last step, we need to get the address of the tile B. And we know that the tile B is near him. We can find this tile, change tile around it. Because we get the address of the tile A and B, we can subtract to get the length of the level. That is 420. And divide it with the entire size of the buffer. We get the height of the level. Nice. Now we can plot it, right?
But, you know, before developing the web app itself, we sort of needed to do some proof of concept because we needed to know that we were going on the right path. So we first started using this library called GIMP, and, you know, because we were using JavaScript. And our idea was just to paint the tile map that we had in a simple bitmap image file to see what we got. And basically, this is how we in this code, we just load the libraries and the tile map. And part of the code is because we need to drop the first 3 bytes because they're just some useless header. And then we paint basically with white if the code is 0, 0, and otherwise we paint it with black. And we also need to loop through each byte of the tile map to paint each pixel in the BMP image, but don't mind this code, it's very poor one. It was mostly for our proof of concept. And with it, we saw that it was working, and this was what our very first tile map looked like. But this didn't fit our needs. By the way, you can notice this part here in the corner. This is a scheme, basically a palette with all the tiles that are available for this level. Just to be sure that we were doing the right thing, we tried the same thing for the next level, and again, it worked. And our next step was to, you know, by a very, very boring process, to map each tile ID to a color so that the tile map that we had looked like what it looks like in the real game. So then we started having a pretty tile map. And one gotcha is that each level has a different scheme. So as you can see, this level looks a bit weird because it sort of have grass on the upper side, right, when it should not. Basically, this happens because we are painting, for example, level 2 with the color scheme of level 1, and it took us a little to figure out this. But it makes sense because if all the levels had the same scheme, the entire game could have only 255 different tiles. And even though Clonova is a very, very simple game, 255 is not enough. So this was one gotcha that we had when painting, but by this time we could already paint the tile map with the data we extracted. But then we need to find and paint objects other than simple tiles.
Yes, okay, it's very nice that you can plot the tile map, but a level has more things than just the tile map. It also has objects such as monsters, diamonds, etc. It will be very nice that you can also plot our proof of concept. So let's do it. So let's use again the tool on NoCatchB to understand how the game updates the X position of the monster. And you can notice that this monster is stored as the address 07000008. It isn't a surprise because it's the second object that we have here. Clonal is the first, and each object demands 8 bytes. As we already know that DMA updates the OAM of each frame. So we need to track this value, or better, since now we need to track the X position of the second object because the monster and track the X position of the second object because the monster is walking horizontally and the batch at object of X position is the third and the fourth. We need to track this value now. And we already know that the OM on V1 is updated for those instructions, so we can debug step by step from here to find where is updated the position of the monster. And with it, we can find the instructions that write the X position. And read the assembly code, we can note that it uses a constant value, 03002920. Looks good. Let's go to this address. Hey, this address is the clonous object. It catches our attentions, and this is not a coincidence. Looking for more attention to this bytes behaviors, we can note that we are on a memory segment that keeps the state of all objects on the level, including the objects that are outside of the play vision. We can check each run the game and see the value updated with a consistent pattern. As well as we can grab a monster and see the object of its X position updates as clonous walking. So there is a correlation, and it's very amazing to understand the game. Let's call this memory section as a global OAM, and after to play a little with this memory section, change the value and see what happens, we can understand better how it works. Okay, we find what's the data source of OM, that is global OAM. Now let's run the debug step by step to find what's the data source of the global OAM. Using the same approach, walk into main instructions. We found this another memory section on ROM. This is the initial data of the objects on a level. We can see it by not similarities between each and global OAM, and by changing a batch and seeing what happens. And let's call it as a ROM OAM, because it's the sketch of the OAM on a level stored on the ROM. And something very fun is that there is a batch to store the ID of the card object and another batch to store the sprite of this object. So we can use the sprite of a monster in a key object. It's very fun. And another thing is that as well as use the sprite of a hunter on a monster. It's another little very fun to do. This is the information flow on ROM OAM, global OAM, and OAM. And ROM OAM keeps the information about all objects on all stages of a level. For example, the initial position on each stage, the kind of these objects, some metadata. How can we discover what this batch is? Just change the batch and see what happens on the game. It's very fun to do, of course. Okay, we found the ROM OAM of the first level. Where is the second level? Maybe below it? Let's check. And yeah, it's here. And Matheus.
Yeah, and if you get to notice, it's very different to read OAM and read a tile map. While in the tile map, all you have to do is loop through a vector and get to paint the pixels. When it comes to OAM, you need to map different bytes to a JavaScript object in our case. So to make those things easier, we went on NPM because it's JavaScript, so probably someone has written a library for it. And guess what? Someone had written a library for it, and it was called QUnpack because it was inspired by Unpack from Perl, and we did some Perl in the past, so we went for it. But it was not expressive because this code just sounded a little bit weird for anyone who hadn't memorized what the hell is, for example, v2, x4, v2, x4, v2, x4, v2, and so forth, so on. So, thanks God we are not doing some Perl anymore, so we went to find something that is more semantic in JavaScript, and we found there's another library called Binary by Substack, the same guy who wrote Browserify. And then we had a way more expressive code using this pipe-based APIs where we could, for example, .skip and pass some bytes and so on. And using it, yay. besides plotting the tile map, we are now able to plot the objects in this level, and now our proof of concept was sort of worthy. And by now, you guys must be asking yourselves, okay, that's where did all this research took you? So, yeah. Let me just... this is what the web app looks like. Let me move it a little here. And basically you have to pick a game ROM and... Cadê a original?
Você não quer espelhar a tela?
Oh, okay. I better mirror my screen for doing this. Cool. Way better. I can browse files, and here I can get the original game ROM, which can be downloaded in any forum or something like this. And now the UI asks you to select a vision, which is how the game calls levels. And there are only 3, as I mentioned. And then you have the tile map, and we can start. You can zoom in and out the tile map, and you have options like showing or hiding the grid, the portals, and the OAM. But let's start with something simpler. We have an enemy over here, so let's just preventing it from touching us. And you can save the tile map. And wow, right? How my mail? Save to runs, and I'll call it modified 1. You can run it basically in any Game Boy Advance emulator. For example, there's Game Boy JS Online. I rather run it on MGBA, which is one that runs on macOS, and I'll load the m1.gba file. There's some intro, just like any other game. That's okay, yes. And here we have our enemy, and yay, it no longer can affect us. And you can really do something funnier with it. For example, I really like what I call modified 2. Let me show you guys. All this same intro thing, but okay. This one is special. Here you have BalCCon 2019, and I have shit.
Não, assim que joga.
Yeah, sometimes I'm not that good at this game because I got to admit I not really like it, but yeah, I'm about to die. But yeah, you can do so many cool things using it. Let's stop mirroring. Where can I?
Arrange this.
Oh yeah, cool. And let's get a little bit to the coding part. I mean, coding the web app itself. So, again, this. And the first thing to mention is the stack we picked for the project. So, basically, we have React.js because we saw on Twitter that it was the choice. No, because actually the whole declarative way of doing things and the easy state management, and basically React.js is what we do on a daily basis, so what we felt comfortable doing. We have Webpack as a bundler, and we also have Lambda.js as a functional utility belt because its currying just plays very well with the pipeline operator you can get if you use a Bubble plugin. I'll show you in a minute. A little bit about the architecture. So we really appreciate the idea behind monorepos, and we applied this in CloudDBA. So we have two projects, which are Brush and Scissors. And Brush is responsible for the UI. So basically Brush is the React app that renders the tile map and all those things. And Scissors is the one responsible for handling the game ROM. So this is one that extracts data from the ROM and all of those. And in Scissors is where we store the definitions for each level. And they are all JSON-like files, which look like this. You have the run object, which you have a bunch of addresses for tile map, OAM, and portals. And you have the tile map objects, where you have, amongst things like height and width for the level, its a scheme, which is basically an array of the elements you have on the level, like grass, rock, dark rock, woods, and so on. Another cool thing to mention when it comes to coding the web app itself is the usage that we have of WebAssembly, because the flow that Macabeus explained is that we get the tile map compressed, and we use that old C code to uncompress it, and we get the decompressed tile map. But there is no gotcha, which is you can't run that C code in the browser. So we could translate the C code into JavaScript or something, but that would require a lot of extra work, and this was not really our focus, trying to translate this code into JavaScript. So what we did is to use mscripton. I don't know if you've heard of it, but basically mscripton generates the WASM files and JS wrappers around it, so that we can use those WASM files. So what you used it for Huffman and for LZ77. And this is part of our decoding code. And this is another thing I like to highlight. I don't think you can read it, but basically we had a bunch of useless code in the C code because, for example, it's got a main function. It had a bunch of print commands, and those prints were generating useless console logs on the browser, and we didn't need them. Actually, they were bothering us, so we removed the main function. But then the code was no longer running, so we had to make this workaround, which is setting dot on runtime initializing and assigning an empty error function to it. And this is how we uncompress things. We have the compressed file, and it then overrides the original file, uncompressing it. And as you can see, all the communication is based on file system. And we then move the buffer from the ROM to a file called file, and we call the uncompressing function. And one thing that is very puzzling at the first sight is that how the hell are we accessing the file system in the browser? This just doesn't feel safe. And I admit I got no idea why, but mscripton just simulates the file system in a very efficient way. So all of this works thanks to mscripton. Other than that, we had to build a small shell script, just to make it easy to compile things using Docker. And there is a Docker image by the mscript community, and all we had to do is just pass some additional configuration, for example, telling it to include the file system. And then we can Docker run Huffman and Docker run LZ77. And that's the final result, a 3 lines code, JavaScript code, using the pipeline operator that reads the ROM and runs the 2 decompression algorithms. And we felt very happy because this doesn't even look like JavaScript. So thanks to the pipeline operator. A few notes on performance. We got this tile map component as part of our React.js application. And as you may wonder, it's the most important component that we have because it's responsible for displaying the tiles and the OAM and allowing us to edit those. And when we first built it, we used Canva, which is a wrapper around the Canvas API. But then we were having some perf issues. This is the issue that we filed on GitHub for it. Because basically the first load was taking like 3 seconds and the other ones were taking 13 seconds and no one was going to use this. Then we did some performance work on React.js, removing wasted re-renders and all of those things, and we went to 1.8 and 3.6 seconds. And then our next step in optimization was moving from Canvas to WebGL. And then we gained a few more seconds, like 1.6 and 2.8. And then we did some more optimizations on WebGL, and we got both loads taking like 500 or 600 milliseconds. So this is our path recap. We went from 3 and 13 to 1.8 and 3.6 to 1.6 and 2.8 to 0.6 and 0.5 milliseconds. And there's one last challenging thing that we can't, that we have to highlight is the challenge that we have when saving the new tile map. This was one of our most bothering puzzles, challenges. And basically, you have the first level and the second level and so on, and each level is stored continually in the memory. And if you make changes to the first level, then the customized first level was taking was overlapping the next levels. So yeah, this was a problem. And we filed this issue because basically what was happening is that an area vision creating was saving time, overlapping the time map of a vision n-1. And yeah, we got a few slides explaining all of the changes, but I don't really think that we're gonna have time for it. But if you guys are interested in this part of the challenge, reach us out after this talk. But there's a whole thing when it comes to understanding the two instruction different sets that you have in ARM, that are thumb and ARM itself, that you have on ARM v7. But I'll jump straight to the JavaScript code that does it. Basically, our solution was to redirect the patched code to our custom loader, and we checked. It doesn't make much sense saying R0, but we checked if this register was on the table, and if so, we would load an associated value, and then we would return to the original loader. So basically what we did was, using some assembly code and JavaScript code to change the assembly code, we patched the wrong loader with a very custom loader if necessary. Because the cartridge memory had so many empty spaces that we could use to store the bigger levels, the modify ones. This is what the JavaScript code for doing it looked like. A few highlights is, for example, this is where we changed the instructions from the game to ours, and yeah, it's a little. And inside this for each, we have basically an if we checked if there is a custom tile map or not, and if there is, we redirect to ours loader. And another thing to be noticed that sometimes we have .set passing a array of 2 elements, and sometimes we have a .set passing an array of 4 elements. And this basically happens because, as I mentioned, many games use both instruction sets. So 2 arrays were the thumb instructions and 4 arrays were the ARM instructions. But again, if you want to know a little more about that, we can certainly go after. And a little more on the results, not only the web app itself, but the community results. We started spreading the word on Discord and other media on the interwebs, and people were asking questions and doing some good stuff like painting the Brazilian flag, and people wanted to contribute and they were making changes. For example, this guy, He's a speedrunner, and he made a level where you are forced to use speedrunner techniques, otherwise you can't go through the first level. A little bit about the future. Basically, we intend to keep refactoring and improving code, adding some functionality, and isolating parts of the code into new libraries. So, for example, we intend to have this what we call React Exe, which basically looks like Hex Editor New, and the React Tile Map, which basically looks like Child from RPG Maker, if you've ever played with it. He is Bruno Macabeus. He's doing right now some full stack stuff at Cat Safari, and he's the guy who's always having an idea of creating new projects and those crazy stuff. I am Matheus. Right now I'm a front-end engineer at TRV in Prague, and I'm the one who's addicted to emojis, memes, and beers. So reach me out for, what is it called? Haika? Some beer at the conf. There's Benjamin, who's over there, and he helped a lot translating posts and giving feedback on the talk. And there's Raul, who's the guy who made the logo. This talk is available at this link on Speaker Deck. Again, the project is available on GitHub. There are a bunch of blog posts explaining in details how we did that. And they are written in Portuguese, but there is a translation going to English and Spanish, so we have many posts in English so far. Last but not least, we got stickers. And that's it, guys. Thanks, or have luck.